Welcome back, everyone. This is the third lecture on distributed deep learning. So far, what we have covered is the necessity of using deep learning. We also covered the part of what is the impact of different kinds of system topology. And we saw a demo of on a machine which is called a DGX-V, which is consisting of 8 Volta cards. And we saw the impact of latency and throughput and the effect of using peer-to-peer transfers using NVLink versus a non-NVLink based system, and how the scaling can get impacted. We briefly covered the usage of NGC and how TensorFlow and Horovod kind of support distributed deep learning. Today, we will go slightly deeper into two frameworks. One is TensorFlow, another is Horovod, and we will look at a demo of it. Followed by, in the end, we will look at what kind of a problems that you can face when you start using distributed deep learning and what convergence problems can come, how the accuracy get affected, and how you can solve some of those problems as well. So let us get started. And with this, we are going to start with distributed training in TensorFlow. So as we said, all of the frameworks support distributed deep learning. This one is particularly referring to the TensorFlow APIs. If I look at from a point of view of this support, basically it has multiple implementation. And these implementations are based on two types or two axes. One is synchronous versus asynchronous, and the second one is based on the hardware type that you are going to run this particular strategy on. So in the synchronous versus asynchronous, we have touched this in the previous lecture. In the synchronous training, all the workers train over different slices in a synchronous fashion, and the gradient aggregation happens at every step. While in asynchronous, all the workers work independently, training over the input data and updating the variables asynchronously. Again, the second axis is hardware platform. TensorFlow supports multiple hardware. It supports GPU, it also supports distributed training across CPUs and also on cloud TPUs, which is the tensor processing units by Google. So TensorFlow supports total of 5 strategies that we can use on the GPUs. There are more strategies that ones can be used for accelerator, more like for Google TPUs and all. But we are not going to touch upon them in this particular session. But let me go through the ones which are useful for the accelerators. So the first one is the mirrored strategy. I've kind of highlighted some of the keywords. First is it is synchronous in nature. It creates the replica per GPU. So one of the key things is it's part of the data parallel, and you can see it will create a replica per GPU, and each variable in the model is mirrored. And the variables are always kept in sync. And that's what mirror strategy works on. Multi-worker mirror strategy, as the name says, the keyword there is multiple workers. So it is very similar to the mirrored strategy, but it creates multiple worker, each with potentially multiple GPUs. It creates, similarly to mirror strategy, copy of all the variables in the model on each device and across all the workers. There is another strategy which can be used, which is central storage strategy, where the variables are not mirrored. The updation of the variables or the main copy of it is kept or placed on the CPU, and the operations are replicated across local GPUs. So if there was suppose only one GPU, in that case it will reside only on that particular one GPU. Parameter server strategy we had covered to a certain extent last time, and it is a common data parallel method to scale up, and it kind of helps because all the workers are not talking to each other while they fundamentally talk to a parameter server, and it consists of multiple workers. So the variables are created on the parameter servers and they are read and updated by the workers in each and every step. Another one is one device strategy, where you can define where to place all the variables on which particular single device you would like to put them on. So let's look at the steps which are required inside TensorFlow to convert your normal training to a distributed training. So the first step in this particular example that we are showing is, first of all, we are using a mirrored strategy. And here you can see the first thing is we are defining the strategy ourselves. The second step in this particular session, in this particular approach, is to bundle your existing model within the scope of that strategy. So you can see here that we are saying within the strategy dot scope, I'm going to define my model. So that model is defined within the scope of that particular strategy that you have chosen. If you are not using the distributed strategy, if you're doing it on a normal one GPU, this step is not required, right? You would directly start creating your model layers. So you can see it's quite simple to do this. And the TensorFlow kind of makes the scaling very, very easier by only a few lines of code. We'll look at the code into more details later also. But before showing you the hands-on part of it, let me also introduce you to another framework, which is Horovod, and then we will look at the demo of the Horovod and TensorFlow, both of them. So Horovod basically is a library for distributed deep learning. It was initially a tool for internal use at Uber, which was later open source for the community. Apart from the features which we have, it also have additional tools such as Horovod timeline, which can be used to analyze the time taken for each operation and optimize accordingly. So you can see what all features it has. It supports in the backend, it supports TensorFlow, it supports Keras, PyTorch, Apache. So you can think of Horovod as a meta framework over existing frameworks like TensorFlow, PyTorch and all. It is very easy to install. There's almost minimal code changes that you have to do. And Horovod has been used for multiple exercises and for even doing exascale kind of computing. And it uses some advanced techniques to do really good scaling, or it has different types of optimizers which are used in those scenarios. So Horovod has been used widely and is proven to be scalable across, as I said, thousands of GPUs and nodes. This is from a paper, Exascale Deep Learning for Climate Analytics, and the model was trained on the Summit supercomputer. With that, let us now move to scaling our training script using Horovod. But the key point again that I would like to harp here is that this is like a petaflop simulations and the number of GPUs across which it was run, and you can see it is scaling pretty well. Horovod actually takes its I would say motivation from something called as MPI. MPI stands for Message Passing Interface. It is one of the most prevalent distributed computing model in the high performance computing environment. Who are working in molecular dynamics, computational fluid dynamics, and all those kinds of high performance computing domain. If you want to scale or if you want to distribute your work across multiple nodes, the model which is used is message passing interface. And Horovod uses the MPI model, where each multi-CPU thread would be launched, each of them corresponding to one GPU, which is very different from the TensorFlow case, where one CPU thread was used to handle all the GPUs. This was a design choice by the Horovod team. And it is very, very critical to understand this, because this is one of the fundamental reasons why Horovod can scale really, really well. The steps which are required in the code to make use of Horovod is obviously like MPI, we need to do initialization. Initialization is key to finding out different aspects behind the scenes, and Horovod kind of sets the context there. Then you pin each GPU to a single process. So you would define you at runtime, you will define how many processes you want, and then for each process you will pin a particular GPU. So you can pin one or more GPUs to a single process. Like TensorFlow, again, you're going to wrap the optimizer also inside Horovod distributed optimizer. So you're going to wrap the existing optimizer onto the Horovod distributed optimizer, which will be responsible for calculating or delegating the gradient computation to the original optimizer. So it does the gradient calculation to original optimizer, whichever is there, but it takes the responsibility of averaging the gradient across multiple processes using MPI features like all reduce, all gather, which are very well known in the MPI community, and it is proven to be working really well with different kinds of topologies using InfiniBand like structure and all, and then applying those average gradients. And once it is done with that, so it's basically broadcast the initial variable states from rank 0 to all the other processes. And if you want the code, you will have to change certain code to save the checkpoints and other things only by worker 0. So you don't want all of the workers or all the processes to save the checkpoint, because the same state is maintained by everyone. So there is no need of everyone writing to the same checkpointing values and corrupting them in short. So from a code point of view, this is how it will look like. We first import and then we will initialize the Horovod for the entire script. We then are going to pin the GPUs to a single process. And you can see here the code, which is we are first of all getting all the listed devices available. We get that particular list, and for every GPU, we are basically based on the rank of that particular process. Like the process when you're launching inside Horovod, if you're launching two processes, there will be process 1 will get a rank of 0, process 1 will get a rank of, process 2 will get a rank of 1. So based on the rank which every Horovod process gets, you would do set visible device, which means every process will get its own GPU. In TensorFlow, the strategy API would handle the of the weights and making identical updates. But in Horovod, we can use the optimizer of our distributed optimizer method. Updates are identical and are kept in sync. So if you see here, we can choose our own optimizer and then wrap that optimizer inside the distributed optimizer. So the current optimizer will continue to work, but the distributed optimizer, as we said before, responsibility there for it is to make sure that it will basically take over and do the all reduce and all gather part of it, and then do the averaging of the gradients. And then you can also define callbacks from rank 0 to all the other processes. The last but not the least, we already said to you that you can save checkpoints, and we would ideally like only one worker and worker 0, so that to prevent the other workers from corrupting them. So you can say only if my rank is 0, then only I am going to basically save my checkpoints via basically a hook. So this is what kind of completes the flow of the Horovod part of it. Let me take you to the live, as into the code, so that you get an idea of how it looks like. So we are going to continue from our session which we did last time also. So if you remember, I launched the start here. notebook. In the start here notebook, we basically went through the part of the concept or the necessity of distributed deep learning. Then we saw the system topology and what was NCCL, how it was impacting the performance. And today we are looking at the TensorFlow and Horovod implementation. So again, I'm not going to repeat the theory part of it, which I just explained in the method. So the all of these notebooks where they exist would be provided to you on the Slack channel. The link would be provided. These are all open source notebooks. You can go ahead, download them and try them in a multi GPU environment. You would require at least 2 GPUs to get a feeling of how you can distribute the work across multiple GPUs. Within a single GPU environment, these labs will be of almost of no use. As we showed you earlier, there are different kinds of strategies. Like what we didn't show you was there's a different strategy for TPU, which is Google's TPU, and you can run it and set it in case you're using any other kind of a hardware as well. So let me just start running the code one by one. So like the previously, we are importing the TensorFlow, then the Keras. If you remember last time, if I will show you the terminal once, this particular yeah. So if you remember this particular machine, it has basically 8 GPUs, and you can see here 1, 0, 1, 2, 3, 4, 5, 6, 7, and we also talked about how to see okay, so there is a lag which is happening. NVIDIA SMI Topo -M will basically show you the system topology as well. So we are in a machine where we have 8 GPUs. So here you can see that I have set the CUDA visible devices to all of the available GPUs, and we are again running the fashion MNIST dataset, so we don't need to worry about that part. So it just downloads the fashion MNIST dataset. So the first step that we discussed in the TensorFlow was to define the strategy. Here, as you can see here, we are saying TF of distributed mirrored strategies. We are adopting the mirrored strategy here, and you can see what it will do is that once you run it, it will try to, you can use number of replicas in sync. You would, what all GPUs devices, how many of them are visible to it can be seen by this. You can see here, it can see almost all of the devices, which is the 8 devices which are available. After this, let us run the code again. So this particular code is basically code to just do some additional task of defining the batch size. For each and every replica, you're going to have your batch size, and then you're going to basically just give it. So there's nothing so great about this code. You can just look at the code and just, here we are trying to shuffle the data for the training and the test set. After you're done with this, you would see that we have to define the scope, and you can see here within the scope here, we are creating the model. So the model is a traditional convolution neural network model, and the main idea here is to get it inside the scope, and then within you can define your hyperparameters like what's the metric and what is the optimizer and all those things here. So here we are using the Adam optimizer in this particular case. Once you're done with that, you can basically call the model.fit function, and it is ideally supposed to run across all of the GPUs. So again, you can see here it is using NCCL. So it will still use NCCL as we had shown you last time, and it will start the job. So you can see here it has already finished, and the images per second is almost 2,13,891. Um, so it was quite easy to run it on a TensorFlow environment. Practically, your code does not change so much. I'm going to just run this particular cell because TensorFlow kind of does a greedy allocation, and it won't allow us to run the Horovod simulation. So I'm just shutting down the kernel just to make sure we have freed up all the space. So this was a very quick demo of how to use TensorFlow. Now we are going to move towards Horovod. So Horovod, again, I have told you that it takes its motivation from MPI, which has been the most scalable distributed framework that we have seen in the high performance computing domain. But it basically has to make sure that it kind of adheres to certain principles, like pin the process to its own exclusive GPU. So every process is going to pin itself to a particular GPU. It will utilize a single rank for broadcasting values that needs to be used uniformly. So a single rank needs to be used for broadcasting the values. Utilize a single rank for collecting the values and reducing. Because without this, there would be a problem in terms of the accuracy. So utilize a single rank for also logging and writing to the disk. So generally, this is done by your primary process or the rank 0. And I will show you what do I mean by that, right? So you can see here, you're first doing the initialization. After the initialization, basically, the second thing which we told is you have to set the set visible device, and it is based on the rank. So the rank 0 will will use the GPU 0. Rank 1 will use GPU 1. That's how it uses. And then you will define your own distributed, you will wrap the optimizer onto distributed optimizer. So let's look at the actual code here. So again, you can see we are using Horovod, but we are using within Horovod still TensorFlow. As I said, that Horovod is basically a higher level framework. It can work on different backends like PyTorch and other methods also. Here we are still using Horovod, but over TensorFlow. But if you write code in Horovod, it can use any of the backends. So let us use initialize. The first thing that we are doing here is to initialize the Horovod. So till the time it is running anyhow, the second thing which we told was to set the visible device. This is very, very critical. Otherwise, you will all end up using one single GPU. And we are doing the same thing. We are creating the data sets and creating a replica of it too. So let it run. It's taking certain amount of time. After you're done with this, as you can see, you're creating your normal model, which is in this particular case, we are building the model with a couple of layers: convolution, max pooling, dropout, and then we are also defining a normal optimizer. Here in this case, we are using the Adam optimizer for doing this. After we are done with the Adam optimizer, we are doing Horovod.distributed optimizer. So we are wrapping the existing optimizer within the distributed optimizer, and it takes certain flags like how many backward passes you need per step, or average aggregated gradients. Do you want average gradients or not? And we have set this to true, obviously. And then we compile the overall code. Let me check. It is still not finished. Let me just restart the kernel. After you're done with this, after that, I think we have just written some wrapper to figure out how many images per second we are able to calculate using the throughput and the callback that we are going to provide it with. So this is the callback that we are creating. to calculate the how many images per second we are able to work on. And in the end, yes, again you would do model.fit. So you say model.fit, and you basically provide it with the same thing. So you basically are saying this. So let us see if anything has happened. It seems to having some problem to run forward. Okay, so it started working now. Great. I don't know what's happening. So there is some refresh problem. Actually, it's not the problem of this thing. So I hope the code was kind of clear with respect to model.fit here. This is going to run basically one optimizer here on one process only, and you can see it's like 67,000 something, right? So let us stop this as well. So we have just restarted it, and we are going to now run the Horovod with multiple number of processes. You can see here, I'm running the same code, but this code, I can define the number of processes. So if I have 2 GPUs, I can set -NP2. If I have 4 GPUs, I can set -NP4. If I have 8 GPUs, I can set -NP8. So based on the number of GPUs that you have, you can basically run this, and ideally it is supposed to give you the scaling efficiency that you are expecting out of it. So there is some problem running this code on this machine, but hopefully it will get through in a bit. So let it run till the time we'll go back to the theory part, and hopefully we have got an idea of how to use both Horovod and TensorFlow.